Now that we've reviewed a little bit about formal charges in line bond structure and valence electrons, we can dive into resonance because resonance is really all about the movement of electrons in a molecule. So we want to review what is resonance, what have we learned about it before, and how can we carry our knowledge about it forward into organic chemistry. So resonance structures were drawn in general chemistry when we were drawing Lewis structures, and one Lewis structure was not adequate or could not adequately represent the overall picture of that molecule. So often you would see molecules that had double bonds with single bonds or triple bonds with single bonds. And those electrons could be relocated in different spots around the molecule. And then we used special resonance arrows between the resonance structures. But really what we were showing was the delocalization of electrons. And that's important because the electrons were not localized or stuck between two specific atoms. They could be moved around, which is what delocalized means. When we have atoms and the electrons can be moved around in those bonds without breaking any rules, then we want to draw resonance structures for them. And so we're going to kind of learn some basic patterns to look for when you are starting to figure out resonance structures that will help guide you for drawing them. Let's look at something called the allyl carbocation. So we learned what a carbocation was previously. That's a carbon with a +1 charge on it, and it actually has 3 covalent bonds instead of 4. So this is called the allyl carbocation right here. We're going to see how we could draw resonance structures for this molecule. So remember, if you were looking at this longhand, you would have carbon double bonded to another carbon, bonded to a single carbon here. How many hydrogens are coming off at the end on the left? We have 2 hydrogens coming off there because that carbon would have 4 bonds. The middle carbon would have 4 bonds, and so that would have 2 carbons coming off, or 1 carbon coming off of there, sorry. And then the carbon at the end, that's a carbocation we know. It has a +1 formal charge, so how many unwritten hydrogens must be coming off of there? Normally, a terminal carbon would have 3, but in this case, there's just going to be 2 coming off of here. Before we can dive right into drawing resonance structures, let's work our way up through a little bit of review. First, let's think about what the steric number, or sometimes called the electron cloud number, is around each carbon in our allyl carbocation. The steric number is what you would have figured out when you were doing VESPER. It's how many sigma bonds there are, or bonding sites around that atom, and how many lone pairs are on it. So we just drew out our carbons and our hydrogens. So we said there was 2 hydrogens here, 1 hydrogen here, and then 2 hydrogens coming off of here. So notice on our first carbon right here, that carbon is bonded to 3 other things. It's bonded to hydrogen, hydrogen, and then this carbon here. So we would say that that carbon is AX3, meaning the steric number is 3. If we look at our next carbon right here, that carbon is bonded to hydrogen, carbon, and carbon. So this one right here is also AX3. Steric number would be 3. Now, as you saw from chapter 1 when you were reviewing general chemistry, when you have a carbon that is part of a double bond, that is typical of a trigonal planar carbon where it is AX3. What's different is our carbocation, where carbon has only single bonds, is normally an AX4 carbon. But since it's a carbocation, that carbon is bonded to 1, 2, 3 other things. So a carbocation actually also has AX3 geometry and a steric number of 3, just like the other 2 carbons in this allyl carbocation molecule have. So that makes it special. That makes it able to participate in resonance. What is the hybridization of each of our carbons? All of them are AX3, so when it's AX3, the hybridization of every single one of these carbons is going to be the same because they all have the same geometry. All of them are going to be sp2 hybridized. And when they are sp2 hybridized, that means that there is one unhybridized p orbital that each of those carbons will have. And that's what this picture is showing us. We're not seeing the sp2 hybrid orbitals. We're seeing that red and blue unhybridized p orbital that is present on all three of those carbon atoms, including the carbocation. And that's important to have that if you're going to have resonance at all. If electrons are going to be able to delocalize or move throughout different atoms, then you have to have at least an unhybridized p orbital, which we have one on each of our three carbon atoms in this example. So here is a little bit of a bigger picture of what we were just looking at. In our Allyl Carbocation, which so that carbon would have been the one with the positive 1 charge in it, we have 3 unhybridized p orbitals, one on each of the carbon atoms. And the electrons can actually move throughout this space right here. They can move throughout these unhybridized p orbitals. And so that is resonance. When those electrons can delocalize and move throughout those p orbitals that are unhybridized, that lie above and below that plane, it allows them to pass throughout and not be localized in one location. So now let's back up and actually show our resonance picture or our resonance structures for that Allyl carbocation using line bond. So we started with this. We had a carbon that had a positive charge. That was our carbocation. We had a double bond right here. And recall that whenever you're drawing resonance structures, you have a resonance arrow in between them. And a resonance arrow is a double-headed arrow. So if it has a single head to it, that would be like a reaction arrow. So make sure that you're drawing resonance arrows. Now, just like we learned in general chemistry, we could take these pi electrons and we could place them between the other 2 carbons. So our resonance picture would look something like this. We could have a double bond here instead, and then that would make this carbon at the left-hand side the carbocation. And later we're going to learn some rules and some patterns for you to be able to figure out how to actually move those electrons right now. But this is a pretty simple molecule because there was only one other location where those pi electrons could have delocalized to. And it essentially just looks like the mirror image of that molecule. But what we're trying to show is that those electrons could either be right here or they could be right here. So one picture didn't fully accurately represent that, which is why we draw resonance structures. There are 2 ways that you might see resonance structures depicted. You might see the contributors or you might see the hybrid. So resonance contributors are what you would be most familiar with, which is the picture on the left here. We're showing both of the individual contributing structures. Sometimes one structure could be better than the other. Sometimes they're equal. In this case, the 2 contributing structures are equal. They're no different than one another. But really what that means to us when we think about, well, what does this molecule look like in real life? Well, it's not alternating back and forth between these 2 structures. It's not like an equilibrium where it's flipping. It's really a hybrid combination of both of those structures. So some people like to draw something called the resonance hybrid, which really what that means is between each of our carbon atoms, there's not one single bond and there's not one double bond. It's more like a 1.5 bond between each of those carbon atoms. So that's what these dashed lines are representing. And then each carbon on the end could have a slightly positive charge to it, rather than just one side having it. So the hybrid tries to depict a picture combining both of the contributors together. Usually, 9 times out of 10, you'll be drawing out the individual resonance contributing structures rather than putting them together and seeing a hybrid. Resonance is an important concept when discussing the stability of molecules and why sometimes reactions go forward in the direction they do. So having resonance makes a molecule more stable. It's a good thing to have resonance. Delocalization of electrons is the first reason. Electrons exist in orbitals that span a greater distance, giving the electrons more freedom to kind of spread themselves out, minimizing repulsions between them. So that's a good thing. They can minimize the amount of repulsions they have. And electrons will spend time closer to multiple nuclei. So since they can spread out, they can get closer to different nuclei of different atoms, and that maximizes the amount of attractions that they can have. So delocalization minimizes the amount of repulsions while also maximizing the amount of attractions. So that's one reason that it's good and it leads to extra stability. The other thing is the delocalization of that charge. So the charge is spread out throughout the molecule, or at least part of the molecule, rather than being localized on only one atom. So like we saw in that resonance hybrid, the partial charges are more stable than a full positive charge on something, like you see when you're looking at one of the resonance contributing structures rather than the hybrid. But just think about if you have charge, whether it's a negative charge or a positive charge, it's good if you can spread that charge out over multiple atoms rather than having it stuck on one atom. How we show reaction mechanisms and how we show moving from one resonance structure to another is through the use of curved arrows. Curved arrows are always used to show electron movement, nothing else. All arrows indicate is electrons going from one thing to another. So before we actually do reaction mechanisms in this class, it's good to use curved arrows first to learn resonance, because we're not actually doing a reaction or changing something to something else. We're just sticking with one molecule and looking at how electrons could move throughout that molecule. When we show our movement of electrons, we're always going to move them in pairs for now. We will learn something later called radical reactions, where you could have an electron moving alone as one electron, but for now, when you see a curved arrow, you should assume that it's showing the movement of a pair of electrons or two electrons together. Where the arrow starts at, or the beginning of the arrow, is where the electrons are currently located. And where the arrow ends at is where the electrons are going to. So previously, when we were looking at that allyl carbocation, we just drew the two resonance contributors, but we didn't show using a curved arrow how the electrons would have moved from one location to another. How did those pi electrons, those loosely held electrons in the unhybridized p orbitals, get from one spot to another in that molecule? And that's what we want to use the curved arrows for. So curved arrows are always going to be a double-headed arrow. So you show the full double head on there, and that's because that represents specifically two electrons being moved. So in this example, we have a molecule very similar to our allyl carbocation, except for we actually have an extra carbon down here. And remember, that would be a CH3 group. It's not a carbocation. Only this carbon is right here. And then how many hydrogens would be coming off that are not being shown at our carbocation? That carbon would have 3 bonds total, so that means that there would just be one unshown hydrogen right here. Now, this arrow is trying to indicate that the pi electrons between this carbon right here, and our carbocation can move over and form a double bond in between these two carbons, which would then change the location of our carbocation. So if we're going to draw the full resonance structure of this molecule, we would use our double-headed arrow, our resonance arrow. We would have our 4 carbons right here. And then we would have a double bond now in between these 2 carbons, because that's what our arrow showed. We pushed those pi electrons into their new location. And how many hydrogens were coming off of the end here? We had 1, 2, because that carbon would have 4 bonds. Well, those 2 electrons are still there. And this one, or those 2 hydrogens are still there, and that 1 hydrogen where the carbocation one is still there. Well, now the carbocation is going to have a new location. It's going to be right here, because that carbon at the end only has 3 bonds to it. So if you started with a carbocation, you're most likely going to end with a carbocation. It's just going to be in a new location when you have this kind of a resonance pattern. So those would be our 2 resonance contributing structures for this molecule. Our double bond can't go anywhere else. If we were to push it anywhere else, we would be breaking the octet rule. So really, it's only moving throughout those carbon atoms that have those sp2 hybrid orbitals on them. So now let's kind of go through some rules and some things that can help guide you when using curved arrows to show electrons moving in resonance. So a curved arrow always represents two electrons moving, and they can only go to certain locations in the molecule. You can't put them just anywhere. So first and foremost, avoid breaking a single covalent bond. If you break a single covalent bond, you are essentially going to be making something that is less stable, that really wouldn't exist in real life. Single bonds can break in reactions, but they're not going to break in resonance. So for example, imagine you wanted to take the two electrons right here, and then you draw your curved arrow and you were going to push them over here. Well, that would essentially cleave or break that carbon-carbon bond right here. And you would end up with a carbon-carbon double bond where you pushed those electrons. That formal charge would go away right there. But then you would have formed another fragment where that carbon on the other side has essentially a +1 formal charge. So don't do that. You don't want to break a sigma carbon-carbon single bond. Single bonds, we'll see, we can break them sometimes, but never break them when drawing a resonance structure. The next rule to help guide you is to never exceed an octet for an element that's in the second row. So for example, boron, carbon, nitrogen, oxygen, fluorine, all of those are in the second period of the periodic table, and so they cannot exceed an octet. Certain elements, when they were in the third period, fourth period, fifth period, so third period and lower, they could have expanded octets around them. But because elements that are in the second period have a 2s2, 2p6 maximum for their valence shell, they cannot have more than 8 electrons in their outermost orbital. So they cannot exceed an octet in that second period. So let's look at some examples where the arrows are bad, and these would not be resonance arrows that you should draw. So for example, on the left, we have an oxygen that has a negative charge, and it has a lone pair of electrons. Those electrons you might think could delocalize and move in between the carbon and the oxygen, and you would maybe draw something like this. Double bond here, carbon, hydrogen, hydrogen, hydrogen. Your oxygen would be left with two lone pairs on it. And now your oxygen would technically have no formal charge, and your carbon would have a negative formal charge. But notice the carbon has 5 bonds around it instead of 4. Don't ever draw 5 bonds around carbon. You are exceeding the octet for carbon, and it cannot do that. So this would not be a resonance structure, these two structures. That's an inaccurate way to draw that because you've exceeded the octet on carbon, so you cannot draw that. The next two are also bad arrows. Nitrogen is in the same period as carbon, and so it also cannot exceed its octet. Nitrogen, even if you don't see them, remember has that lone pair of electrons on it when it has 0 formal charge, and it's trivalent, so it has 3 bonds. So it already has an octet of electrons around it. If you were to try to push one of these lone pairs over and draw this, now nitrogen has 4 bonds and a lone pair of electrons around it. So when we were to look at the formal charge, we would have 1, 2, 3, 4, 5, 6. Nitrogen would have a -1 formal charge here, and it has technically 2, 4, 6, 8, 10 electrons around it. So it's exceeded its octet. That would not be a resonance structure. And then same with the last one also. Oxygen is in the second period, so you don't want to exceed the octet on oxygen as well. If we look at this last structure, which let me redraw this right here, we have an oxygen with 3 lone pairs of electrons, so that means it has a -1 formal charge. Can we take one of the lone pairs right here and move it over here to draw a resonance structure for that? How many hydrogens you want to think are coming off of carbon right here? How many are unshown? Well, carbon would form 4 bonds. It doesn't have a formal charge, so there would be 2 unshown hydrogens right there. Carbon already has 4 bonds to it. If we were to draw something like this, now carbon still has those two unwritten hydrogens right there. So this is an example of carbon having 5 bonds again. So we said that can't happen. And you can even see it kind of looks funny when you look at it. That carbon has 5 bonds coming off of it. And so then it would have a negative formal charge there too. So you're exceeding the octet there. So that would be another example of a bad arrow. And it would not lead you to a resonant structure. Sometimes you might see second row elements having less than an octet. We said they'll never have more than an octet, but occasionally you could see resonant structures where they have less than an octet. So let's imagine that we take the pi electrons that are in between our carbon and our oxygen here, which in this case, we could move those pi electrons to the more electronegative atom, which would be oxygen. And so we use an arrow and we draw the electrons going from carbon up to oxygen. Remember, that's showing 2 electrons. And then our oxygen would now have 3 lone pairs on it. In the left, it has 2, but we moved a pair from in between carbon and oxygen up to the oxygen. And when we did that, we had a structure that was good. This would actually be the better resonant structure. And we made it a worse one. But we're just showing both of them for an example. Because now our carbon is electron deficient, our oxygen is electron rich, our carbon has less than an octet. We pulled those electrons and pushed them up to the oxygen. That developed a carbocation on the carbon, where now it just has 3 sigma bonds to it. And our oxygen has an extra electron surrounding it, and so now it has a -1 formal charge. So we had 0 formal charge on the left, and then we split that pi bond up, we pushed it up to the oxygen, and now we actually have a +1 formal charge and a -1 formal charge. Notice though the sum of the formal charges actually adds to 0. So they add up to what the formal charges were on the left. And that's something you'll see overall. Since this is not a structure that's an ion of any sort, those formal charges all add up to 0 because it's a neutral molecule. When using the curved arrows to show resonance, there will be many times where your structure will have a charge in it, and that formal charge will have to be shown. So just like it was important to show the formal charges in individual molecules, you also want to show them in all of the resonance contributors as well. So if we look at this first example, what would be the resonance contributor? What would be the structure when we push those electrons following the curvy arrows here? So what this first one is showing is those electrons on the oxygen could be pushed in between this carbon and that oxygen. And then we could also push these pi electrons that are in between the 2 carbon atoms over to this carbon right here. Because if we stopped and just left them right here in between carbon and oxygen, then that carbon right here would have 5 bonds to it. So we also have to move the next set of pi electrons as well. So our resonant structure is going to be a combination of those 2 arrows moving. We would have our oxygen right here. We still have our base structure that we'll draw like this. And we're going to have 1 lone pair of electrons left on the oxygen. And then we're going to end up finally moving them. We moved 1 pair right here, and then the double bond that was right here got moved onto this carbon as a lone pair. So I'm showing the lone pairs right now because you're still practicing with that. And then that way it makes it a little bit easier for you to figure out the formal charge if you want to track it. So this set of pi electrons ended up as a lone pair on this carbon, and this set of electrons right here ended up as a double bond in between carbon and oxygen. It doesn't look like anyone is exceeding an octet or we're violating any rules. We can double check. So our oxygen, would it have a formal charge? What would be the formal charge on it? Initially, it had 2 lone pairs and 2 bonds to it, so it was 0. But now it has only 5 electrons around it, so our oxygen has a +1 formal charge, and we're going to show that next to it. Our carbon right here has 4 bonds to it, and so that carbon has 0 formal charge, as does this carbon carbon and this carbon. Those are all 0 formal charge. We didn't even mess with those. But the carbon that has the lone pair of electrons on it, initially that had a double bond there. So there was technically only one hydrogen coming off, and there still is just one hydrogen coming off there. And so that carbon has 1, 2, 3, and then 2 more electrons from the lone pair around it, so a total of 5. So that carbon must have a -1 formal charge. So we went from a molecule that had 0 formal charge to a resonance structure that has a +1 on an oxygen and a -1 on the carbon, which those sum to 0. So that's kind of a little check that you drew the correct structure. And none of the rules that we talked about so far have been violated. We didn't break any single bonds. We only moved pi electrons. Nobody in the second row has exceeded an octet. So our oxygen has two more here, so 4, 2 more here, 6, 2 more here, 8 around it. And our carbon that has a negative charge now, which is a carb anion, has how many electrons around it? It has 2 here, and then it has 2 from the hydrogen, and then 2 more right here from the negative charge where those 2 were moved as a lone pair. So it has a total of 8 valence electrons as well. So we didn't break any rules when writing this resonance structure. You're going to want to be familiar with looking at different patterns in resonance, so we'll break all of them down and look at them separately first. There are 5 main patterns that you'll see for drawing curvy arrows and moving from one resonance contributor to another. The first one is when you have allylic lone pairs. The second is having an allylic positive charge, and that's actually similar to the very first example that we looked at. The third is lone pairs of an electron adjacent to a positive charge, and the word adjacent just means next to. The fourth is having a pi bond between 2 atoms that have different electronegativities. And the last one, the fifth one, is having a conjugated pi bonds that are contained within a ring. So this is important in aromatic compounds. And we'll specifically look at a benzene ring for that one for our example. You might notice that the terms vanillic or vinyl and allylic or allyl are used a lot to describe where something is bonded to in a molecule. So it's important to be familiar with these terms because they are commonly used in organic chemistry. Vanillic positions are when you have something that is directly bonded to the carbon of a double bond. So it's coming right off of that double bond right there. So this would be a vinyl or vanillic position. So would this, so would this, so would this. So if we had something right there, it would be considered to be vinyl or vanillic. Allylic positions are one away from the double bond. So here is our double bond right here. Something in an allylic position is one spot away from that double bond. So if we want to look at this example molecule, can you label all of the vanillic or vinyl chlorides and the allylic or allyl chlorides? So let's start with the vanillic ones. We have a carbon-carbon double bond right here. And notice that this chloro group is coming right off of that carbon-carbon double bond. It's coming right off of this top carbon. So that would be considered a vanillic carbon. Here we have a carbon-carbon double bond right here. This chloro group is coming right off of this lower carbon on the left. That's another vanillic carbon. Let's look at the allylic positions now. So notice here we have our carbon that's part of the double bond, and then this would be, that carbon right there would be the vinyl position, but this chloro group right here is one away. It's one away from the double bond. So this is considered the allylic position, where it's one away from that double bond there. So that chloro in purple that I circled is an allylic carbon or chloro group. And then same thing for this one on the far left. You have your carbon-carbon double bond. This position right here is directly bonded to the carbon-carbon double bond. So that would be a vinyl position. And the chloro group is one away from that. So this would be another allylic chloro group. So we had 2 that were circled in red that are vanillic, and 2 that are circled in purple that are allylic positions. So it's helpful to get familiar with that terminology right away because it's used very commonly. You want to be able to identify lone pairs when they are in a allylic position. So remember, allylic means one spot away from the double bond. So if we look at our allylic lone pairs in this molecule off to the right, we have lone pairs on this nitrogen and lone pairs on this nitrogen. So here we have carbon double bonded to carbon, and these lone pairs of electrons that are on our nitrogen are one away from our carbon-carbon double bond. And that's important because it means that those electrons in that allylic position can participate in resonance. So being able to find these electrons, these allylic position electrons, is key for being able to draw resonance structures. The ones on the top, they are not allylic to that double bond. So these are one away, and then you have your nitrogen, and then they're essentially 2 away from that carbon-carbon double bond. So those are not considered allylic lone pairs, and they are not going to participate in resonance. Let's look at a couple examples here and circle lone pairs that are allylic. And if they are allylic, then we can actually draw the resonance structures and we can show the arrows. So in our first example on the far left, we have a carbon-carbon double bond, and then we have a carb anion. And in all of these examples, because we're practicing, the electrons are being shown. Remember, usually just the formal charge is shown. So if you just saw that carbon with a negative at the end there, you would have to know that there's a lone pair of electrons sitting on that carbon. So those electrons there are one away from our carbon-carbon double bond. So these are going to be allylic electrons. They're an allylic lone pair. And they don't have to be on a carbon for them to be allylic. Just as we saw in the upper picture, they could be on an oxygen or a nitrogen as well. Something like that. Here in our next one, we have a carbon-carbon double bond. And these electrons right here, or these electrons right here, would be allylic lone pairs. Here in our next example, we have a carbon-oxygen double bond. It doesn't actually have to be a carbon-carbon double bond. It just has to be an sp2 hybridized carbon in reality. So it can be a carbon-oxygen double bond as well. And these electrons that are on the oxygen next to that, those are going to be allylic lone pairs. They can participate in resonance. Here we have a carbon-nitrogen double bond. That carbon is still sp2 hybridized. And so these electrons that are one over from that carbon-nitrogen double bond, those are going to be allylic lone pairs. And lastly, we have another carbon-oxygen double bond. These lone pairs are on a nitrogen that is one over from the carbon-oxygen double bond. So those are going to be allylic lone pairs as well. So in all of these examples, these are different ways that you should kind of be familiar with seeing allylic lone pairs. All of these can participate in resonance. So now we want to practice drawing our curvy arrows to show how those electrons would delocalize or move and then draw the resonance picture. So going back to the far left, that allylic lone pair, those 2 electrons could move. We would use a curvy arrow. We have an origin and we have a destination. I started my arrow where the electrons are. I pointed it to where they're going to. Because every carbon has sp2 hybridization, they can move in between there. But then if I just left this next set of pi electrons where it's at right now, this set right here, these 2 of them, my carbon in the middle would exceed an octet. So I'm also going to have to move those to this N carbon right here. So it's going to end up kind of looking like the mirror image of what we have above. So we would have our resonance arrow, and then we would draw our molecule. We're going to now have a double bond right here, and we're going to have a lone pair of electrons or a carbon with a negative formal charge at the very end on the opposite side. So to draw the resonance structure there, that took me 2 arrows when I was dealing with allylic lone pairs. In order to go from one resonance structure to the other, I needed 2 curvy arrows to show the movement of my electrons. And that's going to be one of the main patterns that you see. So next we have allylic lone pairs on the oxygen, and we can take one of those lone pairs, either one, and push it in between the oxygen and the carbon, and then we'll have a double bond in between those two. But then we don't want to exceed the octet on this carbon, so we're going to move these pi electrons to that end carbon right there. So once again, it took me 2 arrows. I'm going to draw my resonance arrow, and then kind of just redrawing the skeleton first. We have oxygen, we have this, this, this. We still have 1 lone pair on the oxygen, but one of them that we moved is now a double bond in between that carbon and oxygen. And then the pi electrons that we moved are now a lone pair on this end carbon, and there's a negative charge there. I can move those there because that carbon was sp2 hybridized. It only had 2 hydrogens coming off on the end. So I didn't break any rules by moving my lone pair to that very end carbon there. And we also want to analyze formal charge. We started with a structure that had no formal charge. Now I have a negative on my lower right carbon, and notice my oxygen has a +1 formal charge. So I have to show that in my resonance structure. Okay, so looking at our next molecule, hopefully you start seeing the patterns here. We have our 2 allylic lone pairs. We're going to choose one of them. We're going to push the allylic lone pair in between oxygen and carbon. And then so we don't exceed the octet on this next carbon, we have to move the pi electrons here up to that electronegative oxygen atom. And so we're going to draw our resonance arrow. We'll draw our skeleton for our structure here. We have this right here, and I haven't placed any of our movements yet. We moved our allylic lone pair in between this carbon and this oxygen, so there's a double bond there now. And our oxygen, now what's not shown actually is in the initial structure, you should know from looking, since oxygen's neutral, it's divalent, it has 2 bonds to it, there's 2 lone pairs that are not shown there. Now, since we moved those pi electrons up there, it actually has 3 lone pairs around it in our new resonance structure. We took the 2 electrons from right here and we pushed them up to the oxygen so that we didn't exceed the octet on that carbon right there. So now we have an oxygen that has a -1 formal charge up at the top, and our oxygen at the bottom still has 1 lone pair on it, but it has 5 electrons around it, so it has a +1 formal charge in this resonance structure. Looking at the 4th molecule, identify the allylic lone pairs. We're going to take our allylic lone pairs, we're going to move them in between our carbon and carbon here, and then to not exceed the octet on the next carbon, we take those electrons, the pi ones, we push them up to the nitrogen. So draw our resonance arrows, and then our skeleton here we got. So nitrogen is trivalent. There is a lone pair of electrons already up there that wasn't being shown, but we know it's there because it didn't have a formal charge. So now that nitrogen has 2 lone pairs on it, and this is a bonding pattern for that nitrogen to be familiar with. 2 lone pairs, 2 bonds. That nitrogen has a -1 formal charge now. And we also moved our lone pair in between this carbon and this carbon before we pushed up that second set of electrons. So in this case, everybody is happy there, it looks like. We've got a carbon that was a carb anion in the original structure. And so that means that that carbon had 3 bonds around it, so 1 hydrogen that wasn't being shown. There still is that 1 hydrogen there, so we're not exceeding an octet or anything coming off of that carbon. And so there's no other formal charges because everyone else is happy, has an octet, and is neutral. You started with a negative charge in the original structure, and you ended up with a negative charge in the new resonance structure. that did not change. So either you have something neutral and it's split into a positive and a negative charge, or if you started with a negative charge, then you still ended with a negative formal charge. It just happens to be on a different atom in this case. Later, we'll learn how to analyze what one's the better structure. But for now, we just want to practice drawing them. And then last one, we're going to need 2 arrows. We got our allylic electrons that we identified on the nitrogen. We're going to push those allylic electrons in between nitrogen and carbon. And then we don't want to exceed 5 bonds to that carbon right here. So we got to take these pi electrons and push them up to the oxygen. Draw a resonance arrow. We want to redraw our skeleton here. We got nitrogen single bond, oxygen up here. Our oxygen had 2 lone pairs not being shown on it. Now it has 3 lone pairs because we pushed a set of electrons that were right here up to the oxygen. And we now have a double bond in between this carbon and our nitrogen from the first lone pair that we moved off of the nitrogen. And we had a neutral structure. I can see we have some formal charges now. Our oxygen has a -1 formal charge, 3 lone pairs, 1 bonding pair. Our nitrogen has a +1 formal charge, 4 bonding pairs, no lone pairs on it. So all of these examples and arrows that we drew were examples of drawing resonance structures when you have an allylic lone pair. So first you got to be able to identify when you have an allylic lone pair, and then you always end up needing 2 curved arrows to push that allylic lone pair.